Have you ever stopped to think about what your computer is actually doing when you're just, using it? Well, today we're pulling back the curtain on its file system. I want you to think of it like a massive, super organized digital filing cabinet, and we're about to figure out exactly how it keeps all your stuff in order. Let's get into it. It really feels like magic, doesn't it? You click an icon and bam, your photo or your document just pops up. But it's not magic at all. It's this incredibly fast, perfectly choreographed dance of data retrieval. And we're going to break that dance down, step by step. So here's our game plan. We're going to start small with the basic building block of everything, the file itself. Then we'll zoom out and look at how files are organized, how they're accessed, and finally, how your computer's operating system acts like a digital librarian to manage and protect the whole system. Okay, first things first. That little icon you click on your desktop, that's just a shortcut, a pretty picture. The real file is a logical container. It's basically a named collection of related information, all bundled up and stored on your desk.
And on the inside, files are definitely not all the same. A simple text file, for instance, is just what it sounds like, a long string of characters. But something like an executable file, a program, it's got a really complex internal structure with different sections of code that tell the computer exactly what to do. So the file's type really decides its internal layout.
You know how a physical file folder has a label on it, right? It tells you what's inside, maybe who created it when it was last updated. Well, digital files are exactly the same. They have this rich set of information attached to them called attributes. So yeah, beyond the name that you and I see, there's a unique ID number that only the operating system cares about. There's its type, a pointer to its exact location on the disk, its size, all the security permissions, and of course, those handy timestamps. This is all the critical info the OS needs to manage everything. So we know what a file is, but what can we actually do with it? Let's talk about the basic operations, the fundamental verbs of file management. Things like creating, writing, reading, and deleting. The moment you hit Save As on a new document, this is what happens in a blink of an eye. The operating system scouts for some empty space on your hard drive. As soon as it finds a spot, it makes an entry in the directory, which is like the master index. And that entry basically says, hey, we've got a new file, and here's where you can find it. The other actions are pretty logical too. When you're writing to a file or reading from it, the system uses a little something called a pointer, which acts like a bookmark to keep track of its place. Deleting is just the reverse of creating. The space gets marked as free, and the entry in the directory gets erased. And truncating is an interesting one. It's like wiping a whiteboard clean, but leaving the board itself there for later. Okay, so handling one file is simple enough. But what about thousands or millions? You can't just dump them all into one giant digital box. You need a system, an organizational structure. So let's look at how directory structures evolved to solve this exact problem. So the earliest, most basic approach was the single-level directory. It's literally one directory for all the files on the entire system. Think of it like one giant filing cabinet drawer for everything. Simple, right? But as you can probably guess, it gets messy. Fast. On the one hand, it's super easy to implement, and it's fast if you only have a handful of files. But the downsides are huge. For one, you can't have two files with the same name, and you can't group related files together. Just imagine trying to find one specific report.txt in a single list with 10,000 other files. No way. So the next logical step in the evolution was the two-level directory. Here, the system creates a master directory, and then inside that, a separate private directory for each user. This is kind of like giving every person in an office their own personal filing drawer. And this was a big improvement. Now, you and I could both have a file called resume.pdf with no problem. But it created a whole new headache. What if you wanted to share that file with me? In this system, you just couldn't. Each user's drawer was completely sealed off from everyone else. And that brings us to the system that we all know and use every single day, the tree-structured directory. This is the one that lets directories contain other directories, creating that nested folders inside folders hierarchy that we're all so familiar with. Now, the tree structure is amazing. It's incredibly organized, it's scalable, and every single file has a completely unique path, like its own address. But it still had one nagging problem. If a file logically belongs in two different places, say in a projects folder and also in a finances folder, you can't do it. Sharing files between different branches of the tree is still really difficult. So how do we finally solve that sharing problem? We do it with something called an acyclic graph directory. Just think of it as a tree structure with a superpower. It allows for links. This means a single file or folder can appear to be in multiple places at once. It's not a copy. It's a shared link back to the one original file. This is the magic behind shortcuts on your desktop.
But here's the trade-off. We get this incredibly powerful ability to share, which is essential for how we work today. But it makes things more complicated. Like, what happens when you delete a shared file? If the system isn't super careful, you can end up with broken links or dangling pointers that are pointing to something that just isn't there anymore.
All right, so we've got our files organized into these amazing directory structures. Now let's zoom back in and focus on a single file again. How does the computer actually read the information that's inside it? Well, there are two main ways. On one side, you've got sequential access. This is like listening to an old cassette tape. You have to start at the beginning and read everything in order to get to the part you want. On the other side is direct, or random, access. This is like a CD or a digital music file. You can jump to any point in the file instantly. You can really see the difference here. With sequential access, the only command you have is basically read the next thing. But with direct access, you can say, go read data block number 87 right now. One is linear, one is not. And modern hard drives, and especially SSDs, are built from the ground up for this incredibly powerful direct access model. So, who manages all of this? Who keeps track of all the files, the directories, the pointers, the permissions? Well, that's the final piece of our puzzle, the operating system itself. It is our master digital librarian. And this librarian doesn't just organize, it protects. The OS defines exactly what someone can do to a file. Can they read it, write to it, run it like a program? And it controls who gets to do those things. For example, you, as the owner, might have full control over a file. Maybe your group of coworkers can only read it, and then everyone else, the universe, can't see it at all. So from a simple double click to this complex web of directories and pointers and permissions, the file system is this elegant, invisible solution to managing digital chaos. The next time you save a document, take a second to think about that invisible librarian working tirelessly behind the screen to make it all happen. It makes you wonder, right? What other invisible systems are quietly powering your digital world?